As we discussed previously, the original art in the dataset doesn't have the BMI values. Maybe that was not even a thing back then. But since we already have the height and weight values for all our participants or most of them, we can calculate BMI from these two values. We'll be using SAS code for that, but the code itself is pretty simple. You can even use a ChatGPT to create that code. We will be writing the code in our existing SAS heart.sas program. We, in fact, I have already entered it, but I'm going to delete it so I can write it again. Okay, so the data that we will be creating, let's make it in capital. Data that we will be creating will be FHS underscore lib dot heart 2, and we will be replacing the existing heart data set, and the set we will be using again will be FHS underscore lib dot heart 2 dataset semicolon, and then we will be converting height into height meters first. So this will be height underscore m, that's the new variable that we are creating, is equal to the existing height, which is in probably inches. So we will just simply be multiplying it with 0.0254. That will give us the height in meters, semicolon. Okay, one thing that you can do is you can, just to remind yourself, you can have some notes within within SAS. But to do that, you can just have /* convert height from inches to meters. Okay, semicolon, sorry, asterisk semicolon. So now this is just for your own reminders. SAS will not be reading this code. Okay, this will just show you next time you are here that what this step entails. Okay, again, we're gonna put a note here, convert, sorry, convert weight from pounds to kilograms. Okay, asterisk / I'm sorry, / and we will be creating a new variable weight underscore kilograms, which would be created from the existing variable weight, multiplying it with value 0.45359. So existing weight is in pounds. So if we multiply it with this value 0.3593 it will convert pounds into kilograms. Okay, now we can calculate the BMI easily. Again, a small note for our remembrance: calculate BMI asterisk asterisk / okay, and if height underscore m is greater than 0, then BMI is equal to weight underscore kilogram divided by height underscore meter asterisk square. So we are squaring that value, parentheses closed, semicolon, and then we end the whole step by a run statement. Let's highlight this code and run this code and see if it runs. All right. Okay, let's look at the log. Everything went very well, so that's great. And let's look at the results. Let's look at the output data. Okay, we see that a new variable BMI is now created at the bottom. And let's see if it has done the job as we wanted. Height and weight. I assume that it has done the job very well, but well, we have to trust the statistical package SAS that it has calculated it well. Go to task and utilities. Under my task, under statistics, you see correlation analysis. Double click on it. We will be using FHS_lib heart2 dataset for this analysis. Our analysis variable would be BMI, and we would like to see if it correlates with, say, age chronic heart disease diagnosis. I am hypothesizing that as the BMI increases, age at which the chronic heart disease diagnosis is going to be lower. And diastolic and systolic blood pressure, I'm assuming that as the BMI increases, the diastolic and systolic blood pressure should increase, and so does the cholesterol. Let's see. Okay, and on the options tab, I am going to keep all the default statistics, but when it comes to plots, I would like to have a matrix of plots, and I would change it to maximum number of plot points being no limit. Okay, so that's all I need. I will submit the code and see what results I get. Okay, so here are our results. We see that as the BMI increases, the age at which chronic heart disease was diagnosed is getting lower. The correlation is minus. You see here it's minus. As the BMI is increasing, age at which the chronic heart disease is diagnosed is decreasing. But this value is so close to zero, it's almost means nothing, right? One thing that we can additionally do is look for the p-values. So let's look for the p-values. Okay, yeah, let's run it again. Okay, now we have the p-values here. Awesome. Okay, so again we see that age at which the chronic heart disease is diagnosed is lowered, but the p-value here is not statistically significant. It is above 0.05, right? These are the number of values that were read by SAS. When it comes to diastolic blood pressure, we see that the correlation is positive, meaning that as the BMI increases, the diastolic blood pressure increases. And this is a pretty strong, moderate size kind of NR, right? And it is statistically significant also. And as we learned in the last video, we need to see both of these values. It has to be statistically significant, and also the value itself has to be of some substantial number. Over here we have like almost 0.4, which falls in the category of moderate correlation between BMI and diastolic blood pressure. Very similar results when it comes to systolic blood pressure. We have a Pearson correlation of 0.36. It is statistically significant. And when it comes to a cholesterol level, well, this falls in the category of maybe kind of not a huge, kind of a mild kind of a correlation between BMI and cholesterol. Nevertheless, it is statistically significant. And we can also visually see that as the BMI is increasing, age at which the chronic heart disease is diagnosed, we do not really see any direction. But diastolic blood pressure, we see some upward trend as the BMI increases, and same goes with systolic blood pressure. And cholesterol, it's difficult to make out, but we do see that there is some upward trend. If we could to find a line which represent all these values, it would be somewhat upward going.